Here's the setup of the Nano engine. Here we have quantum dot with well-defined energy levels, which is capacitively coupled to two leads at the same non-zero temperature. Additionally, the leads are coupled to different environments at zero temperature. So ZL is the impedance of the left environment, and ZR is the impedance of the right environment. Electrons can channel from left to right or right to left through the dot. Due to the coupling to the environment, we can have tunneling events associated to the emission of photons in the environments. I display here such an event where the gray box here represents the quantum dot with well-defined energy levels. The red lines here and there are the Fermi distributions at non-zero temperature of the electrons in the leads. We can have a tunneling event from the left to the dot with the emission of one photon in the left lead, and then the electron can exit the dot while emitting another photon in the right environment. Of course, a symmetrical process may occur in the device. However, if the environments are different, the probability to absorb a photon of a given energy might not be the same for the two environments, giving a different probability for the two symmetrical processes to happen. This will result in a preferred direction concerning the tunneling of the electrons, leading them to a spontaneous current flowing through the device. Let's focus on these physical effects in more details by considering a simple double barrier problem for an incoming electron from the left. The amplitude associated to the transmission of the electron from left to right is given by this expression. An incoming electron can hop from the left region to the middle region, bounce back and forth between the two barriers before exiting the dot to the right region. If we sum over all the different processes, here's the expression we get for the transmission amplitude, where theta here is the phase acquired during one round trip. Now we consider the same process with now the probability to emit photons during the tunneling events. Epsilon L is the energy of the incoming electron, which can tunnel in the middle region and emit simultaneously a photon of energy EB. When it exits, similarly, it can emit a photon of energy EC in the right environment. Here is the resulting amplitude which depends on epsilon L, epsilon R, and omega, the energy of the electron when it is between the two barriers. T, L, and R plus are tunneling elements which are now dressed by the different photo emission processes. Integrating over EL, ER, and omega yields the total current. Let's consider the case where the environments are just one-mode cavities, one LC resonator with impedance ZL and frequency omega L. Here we are at fixed values of the temperature, and we take bare tunneling rate gamma 0 equal gamma L gamma R constant. The red and blue regions here correspond to the zones where the effect is maximal. We remark that it corresponds to the most asymmetric case, not surprisingly. Now we consider the case where we have there is only one lead, the right lead, which is coupled to the environment. We can reach a rather simple expression for the current, which is displayed here. And we study the evolution of the current E, the current I, when varying the frequency of the cavity and the lead temperature.